So these U-try problems kind of follow the notes. So what we'll realize with this first one, this cosine squared theta plus 2 cosine theta equals 3, we want our answer in radians because it tells us, hey, we want our answers between 0 and 2 pi. But like before, you can just solve this quadratic as you would normally factor and then deal with that cosine theta at the end. So remember, we want one side of the equation to equal 0. So I'm actually just going to subtract that 3 right now and make that equal 0. And you can imagine this or work with this as if it was x squared plus 2x minus 3 equals 0 and try factoring that, right? If it's factorable, awesome, use your zero product property. If it's not factorable, no problem, use your quadratic formula. So when I factor this, I'm going to get x plus 3, x minus 1 equals 0. And in this case, what does x represent? X is that cosine theta we're trying to isolate. So I'm going to replace the x with cosine theta. And now I can do my zero product property. So cosine theta plus 3 equals 0, or cosine theta minus 1 equals 0. So now I want to solve for cosine theta. So cosine theta is negative 3, or cosine theta equals 1. So the 1 is actually a lot easier to deal with because we've seen that a lot in the unit circle. So you're thinking, wait, where is x1? Well, x is 1 just at 0 or 2 pi. But since if you look, it says less than 2 pi, not less than or equal to 2 pi, we're not going to include the 2 pi. We'll just stop at 0. Now, this negative 3 is where it's a little more difficult because we don't have a negative 3 anywhere on the unit circle. So you might use your calculator. But before you even look at your calculator, you might want to think about this. Your basic function for cosine has an amplitude of what value? If you think about this, it goes from 1 to negative 1. So if you're trying to graph cosine theta and you're like, wait, where is that y value going to equal negative 3? The answer is never, because it's outside of the range. So in this situation here, this is undefined, right? There's no solution for this. So we only actually have one answer, and that's theta equals 0, because there's no way for our cosine theta to end up being negative 3. Okay, so that's something to keep in mind as we want to think when we're outside of that range or the domain of our function, because that'll affect how many answers we get as well. So it's kind of nice to think about the domain restrictions we talked about when we first went over inverse functions, but also if you just imagine the graph here, right? It just doesn't make sense. Y is never going to be negative 3 because our amplitude is 1, which means we don't go any higher or lower than 1 or negative 1. Okay, next one. Sine squared theta plus 5 sine theta minus 2 equals 0. And here we want our answer in degrees because we're going from 0 to 360. So if you want, it's already equal to 0. So you can imagine this as, hey, how do I solve x squared plus 5x minus 2 equals 0? And just remembering x is sine theta when we come back and put that function back in. Well, I might rack my brain and be like, okay, well, how do I factor this? And I try and I try and I try and I realize, wait a minute, it's not factorable. And that's okay, because now we can use our quadratic formula. So remember, our quadratic formula solves for x, and here our x is sine theta. And then we want to substitute in our a, b, and c. So here, what's my a value? It's 1, right? B is 5, c is negative 2. Let's go ahead and substitute. So negative 5 plus or minus the square root of 5 squared minus 4 times 1 times negative 2 all over 2 times 1, right? And then do your PEMDAS, right? Take your time with it. I'm going to save you guys having to listen to me to run through PEMDAS. But this simplifies down to negative 5 plus or minus the square root of 33 over 2. And then remember that plus or minus means we have two possible answers. So that means sine theta is equal to negative 5 plus root 33 over 2, or sine theta equals negative 5 minus root 33 over 2. And that's clearly not on our unit circle because we're like, wait, what's a square root 33 business? And that's okay. So let's go into the calculator. Oh, sorry about that. But before we do in the calculator, we want to think, wait, what are we doing? We're solving for theta, so we're doing the inverse operation. We're doing inverse tangent. So the inverse tangent of negative 5 plus square root 33 over 2, and the inverse tangent of negative 5 minus 33 over 2 will give me what theta equals. So going into my calculator, I'm going to get approximately, let's go ahead and round this to the nearest thousandth, 21.8 21.856 for that first theta. For that second theta, I'm going to get something that doesn't exist. I'm going to wait. It's going to say there's an error. And let's talk about that in just a moment. Okay, so we did get one answer that worked out in our calculator. We get this 21.856. So before you box it and say, cool, let's move on, remember, we're going from 0 to 360. So if you go back and think about, wait, where is sign positive? Because we're thinking all students take calculus. Sign is positive here because all are positive in the first quadrant. And then in the second quadrant, because students is S for sign. So we should have two different answers. So how do we figure that out? Well, this 21.856 is in the first quadrant, right? This is 21.856. Then where would it be in the second quadrant? We want to do the reflection. So what we're going to do here is basically do 180 minus that 21.856. And that will give me the value that I'm looking for. So theta is not only 21.856, but theta is also approximately 158.144 degrees. Okay, so I know that's sometimes hard to wrap your mind around, but you have to really think about where is sine positive, where is sine negative, and in general for sine, cosine, tangent, right, if you're going from 0 to 360, we should have multiple answers. So that's just something to keep in mind. Okay, so coming back to why is there an error here for the inverse sine of -5 minus root 33 over 2? Well, if we put this -5 minus root 33 over 2 in the calculator, this is actually equal to approximately -5.37228. Sorry if you can't see that, that's 0.228. And then you have to think again, wait a minute, think about your sine graph. Is there any way to find an x where y is -5? Well, sine is like this, right? And if it's just plain old sine, the amplitude is 1. So we're going from positive to -1. So can we ever hit -5? No way. So that's why that's an error. So we only have two answers, which came from that first equation, that -5 plus square root 33 over 2 equals sine theta. Okay, so that's that second U-try problem. All right, moving on to the trig identities U-tries. So again, there's lots and lots of these different types of problems. I can't sit here and do every single one of them. What's important is for you guys to reference your trig identities and think about what you can possibly use. So here, 4 sine squared theta plus 4 cosine theta equals 5. I have a sine and I have a cosine, so I have to think, wait, look back at my identities, which identity kind of puts cosine and sine together and also has a square, right? So then I might want to think, okay, well, I do know cosine squared theta. Let me rewrite that, sorry about that. Cosine squared theta plus sine squared theta equals 1. Now you might be wondering, well, wait, there's a plain old cosine, not a sine, but remember, if we can rewrite everything in the same trig function, so let's get rid of the sine squared. Let's solve for sine squared and put in a cosine squared. Then everything's in cosine. We'll be fine, right? So don't worry too much about, wait, sine's a quadratic, cosine's not a quadratic. What matters is when we plug in our equivalent expression, the original equation is now rewritten with all the same trig function. So that's confusing, don't worry, let me show you the work. So I'm going to subtract cosine squared to both sides. So I'm solving for sine squared theta. It's going to be 1 minus cosine squared theta. So what I can do now is replace sine squared theta here with 1 minus cosine squared theta. So 4 times 1 minus cosine squared theta plus 4 cosine theta equals 5. And now this looks a lot more doable, right? So I can go ahead and distribute that 4. So I'll get 4 minus 4 cosine squared theta plus 4 cosine theta equals 5. Remember, we want one side of the equation equals 0 because I do see it's a quadratic because we have a cosine squared. So I'm going to take away that 5. Actually, I'm going to move everything to the right. So I'm going to subtract this 4, add the 4 cosine squared theta minus the 4 cosine theta because I actually rather not have a negative in front of my cosine squared. So I'm going to put the 0 here on the left. So -4 cosine squared theta moving to the other side becomes a positive 4 cosine squared theta. Positive 4 cosine theta becomes a negative 4 cosine theta. And then 5 minus 4 is positive 1. All right. And now you can ask yourself, is this factorable? Do I have to do the quadratic formula? It's kind of up to you. And if it helps, rewrite this as 4x squared minus 4x plus 1 equals 0, and let's try to factor that. Or of course, if you want to do the quadratic formula, you totally could. But here it is factorable. And remember again, x is our trig function. So x is not theta, x is cosine theta. This does end up being factorable, so this actually becomes 2x minus 1 times 2x minus 1. So I'm going to go ahead and replace the x with the cosine. And what's nice about this is because it's a perfect square trinomial, meaning our two factors are the same, we only have to solve this once, right? Because it's the same. So why do the same work twice? So I'm going to get 2 times cosine theta minus 1 equals 0. Add 1 to both sides. Divide by 2. So cosine theta equals 1/2. And remember 1/2, square root 2 over 2, square root 3 over 2. Those are all things that should trigger unit circle in our brain. So let's look at your unit circle. Where is x 1/2? So x is 1/2 at, I want my answer in radians, so I'm going to write this in radians, pi over 3 and 5 pi over 3. So you guys can see how handy that unit circle really is. Okay? So this last U-try problem involves a double angle, which we didn't talk about before, so it's kind of nice just to be able to use an identity that that's out there. So what is our double angle identity that we would want to use here? Well, it's on your last set of notes, but in case you don't want to pull those out, or if you don't have those handy right now, we know that sine of 2 theta, it's called a double angle because it's 2 times the size of theta, right? So sine of 2 theta is equal to 2 cosine theta times sine theta. And that's really the only identity I can think about working with here. So even though you might be like, wait a minute, you still have a sine left in there, that's okay, let's work with it, let's see what happens, right? Because sometimes it's not really apparent right away what the identity can do for us until we actually start manipulating it. So I'm going to replace sine 2 theta with 2 cosine theta times sine theta, make that equal to negative cosine theta. And then you might be wondering, oh wait, hold on. This is all factors, right? 2 times cosine theta times sine theta. That means I can divide, because remember cosine theta, sine theta are just numbers. So let's divide both sides by cosine theta. Right? So that becomes a 1. This becomes a negative 1 on the right. So 2 sine theta equals negative 1. Divide by 2, and sine theta equals negative 1/2. And now let's just go back and look at our handy dandy unit circle. Where is y equal to negative 1/2? And again, looking at our directions, 0 to 2 pi, radians as my answer. So theta is going to equal 7 pi over 6 or 11 pi over 6. There we go. So that's it for the U-tries. Please let me know if you have any questions. And thanks for listening.